வந்து 7ல் இருக்கும். மேலே போய் ஹலோ மைக் செக். ஹலோ மைக் டெஸ்ட். ராஜி 6ஆம் நம்பர் மியூட் எடுத்துரு. 6 இது மியூட்டு ரிலீஸில் தான் இருக்குது. 6.
Jantar Mantar.
Complex analysis, because real and imaginary part of holomorphic functions are harmonic. Okay, so and also from that it follows that complete minimal surfaces cannot be compact. So for example, a torus can never be thought of, never be immersed into R3 as a minimal surface. You have to remove certain points. For example, torus with 3 punctures, as I showed.
Hello.
Okay. So, and then the most general solution of that equation is zeta is u plus iv, zeta bar is u minus iv, then you can write x of zeta zeta bar in this way, y of zeta zeta bar in this way, and z of zeta zeta bar in this way, where f and g, f is holomorphic, g is meromorphic, such that fg squared is holomorphic, and so basically what I'm saying is holomorphic is it doesn't depend on W, it just depends on W, it doesn't depend on W.
Hello, na pesறது கேக்குதா? நீங்க பேசுறது clear-ஆ கேக்குதுண்ணா.
In that case, you can actually choose your favorite F and G, such that F and G are
நீங்க பேசுறது clear-ஆ கேக்குது.
F is holomorphic, G can be meromorphic, but Fg squared is holomorphic. In that case, you can construct, this is going to be always a minimal surface. So you can take your favorite one. Favorite F and G, only restrictions.
Hello. நீங்க பேசுறது clear-ஆ கேக்குதுண்ணா.
So there's another way of writing it.
Hello.
In a neighborhood of non-umbilical point where the Gaussian curvature is non-zero, any minimal surface can be represented in terms of a non-vanishing meromorphic function. You can actually choose your favorite meromorphic function, and meromorphic function are holomorphic, but they can have poles. They are allowed to have poles. Okay, so they depend only on W, but they can have poles. So yeah, so any minimal surfaces can be represented in terms of one non-vanishing meromorphic function like this. Again, this is always going to be a minimal surface, and you can pick and choose your R. For example, R is equal to 1 corresponds to the inner surface. This corresponds to the catenoid, this corresponds to the helicoid. So all you have to do is pick your favorite R and perform the integrals to get your minimal surface. Okay, I'm not going to go into all these details. So finally, I wanted to tell an interesting fact which me and my collaborators have found, how Ramanujan's identities are also coming in minimal surface theory. So here this is a Scherk surface, type 2, and this is type 1 Scherk surface, right? Okay, so here I have actually performed the integrals and shown. So this was for the helicoid. After performing the integrals, you get that representation I was talking about initially. Oh, sorry, before going into Ramanujan identity, there's a beautiful fact that there is a whole family, isometric deformation from the helicoid to the catenoid, such that this, at every stage, it's a minimal surface. So you see the topology is changing. Here the helicoid has a very different topology from the catenoid, but you can still deform, go from one to the other through a family of minimal surfaces. So that's why this is called the conjugate of this. In some sense, they are actually conjugates of this. So I'm not going into the theory. Similarly, this one and this one, actually there is a way of going from one to the other through a family of minimal surfaces. I have not shown the picture. Actually, I don't have the picture of that. So, okay, finally, how much time do I have? 10 minutes. Okay, good. So, a geometrical interpretation of an identity of Ramanujan. Actually, Euler-Ramanujan I should put. Euler also used to know this. So, tan inverse tan h y cot x is summation k goes from minus infinity to infinity tan inverse y by x plus k pi. Okay. So this is a Euler-Ramanujan identity. This is one of the identities. And but the amazing thing is this left hand side is a height function of a minimal surface. Z is equal to tan inverse tan hy cot x is one way of writing this red. Oh, maybe I have the picture later on. This one. This one can be represented like that. The height function is tan inverse tan h y cot x. It's the Shark's first surface. And these you already, tan inverse y by x you already know is a helicoid, and these are just shifted by k pi. So I have shifted an array of helicoids and
அன்மியூட் பண்ணுங்க. மியூட்டை மட்டும் எடுத்து விடுங்க. Hello. Can the Zoom participants hear the audio? Can anyone please respond? ஸ்பீக்கர் கனெக்ட் பண்ணிருக்கீங்களா? அதுக்கு Zoom ஆடியோ கேட்கிறதுக்கு ஸ்பீக்கர் வேணும்ல? அதான் அப்ப அங்க கேட்கணும்ல? போடுங்க சாட்ல. கீழே கீழே இல்ல அந்த அந்த விண்டோ க்ளோஸ் பண்ணுங்க சார். கீழே சாட் இருக்குமே, பார்ட்டிசிபென்ட்ஸ் பக்கத்துல சாட் இருக்குமே. நான் போடுறேன் இருங்க. Yeah, but we are checking the Zoom audio. Like nobody is responding. We don't know whether they can hear us. Hi, can you hear us? Hello, 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 hello. Hello. Hello, hello. Hello, can you hear me? Hello. Can you see the video? One second. Can you see Vasan? Okay.
Can you hear me?
Yeah. Yeah. Capture कर दो audio input capture कर दो hello 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 இது செலக்டே ஆக மாட்டேங்குது ஹலோ 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 இன்புட் தானே சார் அது எடுத்து விட்டேன் நான் ஹலோ 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 I'm also seeing the chat.
இதை எனேபிள் பண்ணி டைரெக்டாக பேசி பாருங்க கரெக்டாக போதும் போகும்
Hello. Hello. Hello.
இதை ஆஃப் பண்ணிட்டு
Hello. 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 Can you hear now, sir? Hello. 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 You can hear me? Can you hear me, sir? Cordless. This wired microphone. So that is more important. No, if we can hear this, it can be anything.
ஹெட்ஃபோன் இது
Headphone கொடுங்க.
இதில் எத்தனை போட்டிருக்குன்னு பாருங்க எத்தனை போட்டிருக்கு ஆடியோவுக்கு
முதல்ல இங்கே வருதா நான் செக் பண்ணுறேன் ஸ்டாரில் போட்டு கேளுங்க ஹலோ 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 சரி அதை போடுங்க 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 அதை போடுங்க ஹலோ Sir, can you check now? Hello. Hello, hello. Can you hear this noise? No? Hello. Hello, 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 hello. Can you hear? Hello, 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 hello. Hello. Huh? அவர் இருக்காரே மாசன் அவர் கேட்டுட்டு தான் இருக்காரு. வாசன் வாசன் நான் லீவ் பண்ணி ஜாயின் பண்ணுறேன், திருப்பி லீவ் பண்ணிட்டு ஜாயின் பண்ணுறேன் நான். இது எப்படி? Hello. Hello, 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 hello. Hello, hello, hello.
Uh, it looks like we are almost on time, only 2 minutes late, at least from that clock. I'm only checking with that clock. Okay, we said we'll start at 11, now 11:02 or 11:03. So we are very happy to have this BalFest. This year, Bal is turning 85, and it also happens, just for record, he was actually more or less the effective first student of this institute in 1962, when he joined as a student of Madras University. The institute was started in 1962, and this is 60th year finishing, and in fact that's why that IMSC 60 festivals are going on. And he was almost at the ending time with thing, and he actually became a member of Math Science, and then left after a few months to Vienna, if I'm right. So, so it's I'm very happy to have this BalFest 85 festival, and we want to make it fairly technical. That's why it's titled as Quantum Field Theory in Quantum Space-Time. We thought at least it will capture the mood of various things which Bal has been himself working. So it will capture that part. So that is the title which we have. So we had a small committee, Parameswaran Nair, myself, Sanatan, Sujai, Sachin Vaidya, and Ajit Mohan Srivastava. Ayan Mukhopadhyay from IIT Madras. So we had a small committee which discussed, and several other students from here, Vinod Mamle, Tanmay, and who else? There is two more students. Adarsh and Amit, right? And Disha here, who has been helping us. So I just want to put that on record. And Ravindran, who is the director of this institute now, in fact, he was known to all of us as a good friend right from the days. So, because he was here almost as a student, and many of us have moved with him at various levels of his progress, and he has been very kind enough to immediately say, yes, we should have BalFest. And he agreed, and this is the start of the program. He will, after this, he will give welcoming remarks for the program. By 11:10, we should start with the first lecture. The lectures are 40 minutes duration. The expectation is 35 plus 5, but of course 40 can be taken. But since it is going to involve people from outside, Zoom, others also, and to keep the time, I request all the speakers to see to that you complete. I'm sure you cannot complete everything you want to say within that thing, but the essence of what you want to say, so that we have a closure of that particular talk. And of course, people can ask questions during the various times, during that period within that 40 minutes, or outside during coffee time. And also people from outside can send their questions through chat. And there's somebody who is monitoring it, and depending on the time, they will definitely put it to the speaker, or it will be given to the speaker. They will probably respond in some way. So there is the current thing. So I don't want to take too much of your time. Thank you all for coming. And I'm sure you people have traveled, many people have traveled from various places with all their difficulties. I'm sure all of you will have a productive program for the next 4 or 5 days till next Wednesday. And the last day will be towards the end. We have the felicitations for Bal, where a Festschrift book will be released. And then people who want to speak at that time can say something about Bal, either curse him or welcome, praise him. Okay, now Ravindran.
Warm welcome to all the participants of this very interesting program, BalFest. It gives me, in fact, not only pleasure, also pride actually to have such a meeting in IMSC, because Professor Balchandran is known to us for a very, very long time actually. We're from the day one of this institute. He was our student, as you know. I'm also the student, so he was my senior in some sense. I recall, in 87 when I joined this institute as a student, I was just going through our coursework, and I knew some of my seniors, around me, and every day around 11 o'clock, I could see that, people leaving their, or, their, whatever, table or chair, whatever, rushing to some place actually. I used to wonder, where all they go actually. In fact, the people who were going, they were working on different areas in research actually. One was on gravity, other was on particle physics, other one was on condensed matter, but they were all going for this talk actually. I asked him, who is that person who is giving talk actually? Then I came to know that it was Professor Balchandran visiting us. They said Bal, okay? That itself was a strange thing to hear actually, but later on I realized Bal means actually Balchandran. And after that I could see that actually I was also one of them actually later on actually when I actually slightly moved up. So he was one of those actually connected most of our students and faculty at that time, giving a kind of a lecture series on topics which are of interest to most of us actually. And that was the time when I was a student and used to come every summer or whatever to IMSC, and I had seen him all throughout my stay here actually. And after 10 years, not 50, more than 10 years actually, I rejoined, about 10 years back, I rejoined this institute as a faculty. And I see him again actually, and I started seeing him, every year coming, at least, frequency was not that much. And he continued that legacy of, coming here, spending time with all of us, giving, courses and things like that. So in that sense, it's really a pride to have such a meeting in IMSC. I'm happy that, TRG and Sanathan and Sujay and many of you have taken initiative to actually organize this. And IMSC is really happy to be part of this. So thank you for having such a nice meeting, and I welcome all of you again to this wonderful meeting. Enjoy this one full week, and there are a lot of other things to see also in our institute. Visit our library and the other part of the institute. Have a nice stay here actually. Thanks.
Okay, now I request Parmeshwaran Nair to chair this session and then conduct the program.
Thank you, TRG. So I'm supposed to be the chair, crack my whip when it's 40 minutes, and stop you all from talking. But let me first start by congratulating Bal. And there will be many talks showcasing the many facets of his work during the next 5 days or 6 days. So let's start the session without further ado. The first speaker is Denjo O'Connor from Dublin Institute for Advanced Study, and he's going to tell us about multi-matrix invariance. I think you have to go up there. He doesn't need a mic. This one.
Okay. Well, thank you very much for
1 minute.
Thank you very much for the opportunity to speak, and thanks to the organisers for putting such a nice program together and such a warm welcome. And congratulations to Bal for his on his 85th. When one meets him, one is always surprised that he is not in his 30s or something like that. I got to know Bal originally when I was a postdoc in Syracuse in 1987, and his 3 months 316 lectures drew everyone in, and I got captured as part of that. I was part of the gravity group, but still was broadly in BAL's orbit, let's put it that way. And we collaborated more when I took up a permanent position in Mexico later, and I found that he had close connections which predate me by many years to the Dublin Institute for Advanced Studies, where I think he was almost recruited at one point. But that's another story. So I'm not going to take more time. There's probably a second microphone on there. I want to tell you about counting multi-matrix invariants. Bal has heard this lecture already, more or less, but hopefully I have answered some of the questions that he asked at the last time he heard it in this one. Let's see. So, now if I can move on. I think I'll use this. I have a better chance of, if I can, no. Can I just flick page up, page down? No. Space bar? No. It's any of them? Okay. Yeah, if these work, that's fine. It works. This one. Okay, good. You've seen the abstract already. So, I want to tell you, first of all, the context in where these multi-matrix models emerge and part of the interest in them. And I just thought the simplest place to tell you where they emerge is just to consider Yang-Mills in 4 dimensions, 5 dimensions, whatever dimension you want, but I've taken 4 dimensions. And if I compactify it on T3, the tree torus, and I just take the constant modes in that compactification, I get a dimensional reduction of the model, of dimensional reduction of Yang-Mills to 0 plus 1, where time is the only variable left. I get a multi-matrix model, which I've written here below. And it is, the coupling constant is going to be rescaled, of course. So I pulled out the volume of the tree torus from that. And we get this double commutator, which since only the commutators survive, and we've matrices I is equal to 1 up to D, 3, or in the case of standard Yang-Mills. But there's still a covariant derivative left. These are the multi-matrix models. This type of multi-matrix model is what is of interest here. One could dimensionally reduce it to 0 dimensions and get standard multi-matrix models. These variety here would be called multi-matrix quantum mechanics, whereas if I reduced it to 0 dimensions, got rid of time as well, you would have multi-matrix models. And what I'm interested in is counting the invariance of such models. The same action as a curiosity arises if you use light cone gauge fixing and Hoppe-Goldstone quantization of a membrane propagating in 3 plus 1 dimensions. And that's also of interest. If I didn't do the Hoppe-Goldstone quantization, the dt would be a covariant derivative with volume-preserving diffeomorphisms. That's just an aside. It's stuck again. This is not going to work very well. Something. Sorry? Well, it wasn't necessary to point it earlier, but it's just losing. The computer's not responding to it either, you see, so. It's freezing. Zoom is capturing it or something, is it? Okay. Okay, I will. So the invariants, I'm interested in counting the invariants associated with this. So what are the invariants? The invariants are what's left when you do, when you change coordinates for the matrices. In other words, when you do a GLN transformation on the left or right and a joint transformation for a square matrix. You can consider an n by n matrix, and if I consider, I'm just calling X to be a generic n by n matrix. It has n squared degrees of freedom, and there are just n invariants, and of course they are the eigenvalues of the matrix. The eigenvalues are the roots of the characteristic polynomial, Pn, which is the determinant of x minus lambda times the identity. And we know from the Cayley-Hamilton theorem that every finite rank square matrix satisfies its own characteristic polynomial. Pn of x is equal to 0, where Pn is the characteristic polynomial. Pn of lambda would be the characteristic polynomial given by this determinant. If there's a well-known, or should be well-known, relation for generating the characteristic polynomial. It's due originally to Laverniere in 1854, and you can get Pn from Pn minus 1 via this expression here. You see that P1 is a 1 by 1 matrix, so P1 of x is equal to x minus trace of x. That's obviously true. It's going to be 0 if I put in x into this expression. Pn is generated by this iterative relation, and it tells you, since the x satisfies its own characteristic polynomial, Pn of x is equal to 0, and the trace must also be equal to 0. If I just use the trace being equal to 0, it tells me that I can express the determinant in terms of the traces. But if I multiply Pn of x by x, it tells me that trace of x to the n plus 1 can be re-expressed in terms of lower powers. So that's a trace relation. And just to see the content of it, I've just written it out for 2 by 2 matrices. P2 of x is given by this expression, x squared minus the x trace of x, etc. And it tells, we can see that trace of x cubed for any 2 by 2 matrix can be re-expressed in terms of the trace of x and the trace cubed of x and the trace of x squared. For 3 by 3 matrices, I just removed the trace to just show you what it is, and you get this rather simple expression: the trace of x of y to the 4th, y is traceless, is half of the trace of the matrix squared, and etc. These are just trivial things that are very classical. More generally, for an n by n matrix, as I said, you have the trace of n plus 1 is expressible in terms of the traces of lower dimensional ones. And the invariants, the set of n invariants are the traces of x to the power of k, from k being 1 up to n. And these are, of course, completely equivalent to the eigenvalues of the system. The invariance of the matrix, it's useful if I'm going to count how many invariants there are to just put the expressions into a generating function and write down the Zn of t as being the objects that are of interest, this dem n of n, which is what I'm trying to count, and put a variable with it, make a formal polynomial, sum it, and the sum from n equals 0 to infinity of dem n of n t to the n gives me this Zn of t. And if I've just got one matrix, then it's relatively easy to see that I know I have n variables that I'm going to write down. I've trace of x to the k, and I'm forming words in those ones, and the dem n must be given then in terms of the number of partitions of the integer n into capital N or less pieces. And you can then write down that the sum of this is just Zn of t, and you've got a generating function for your expression, and I've written out what it is, and this is it's standard to draw the partitions in terms of Ferrer diagrams. Okay. If I'm dealing with a matrices of creation annihilation operators, you can map the entire system into a Fock space, and we've got again trace of the matrix. Trace of the matrix, trace of the matrix squared, etc. And I've written out the those invariants and how they map in that setting. And again, we can get this partition function by the creation annihilation operators form a basis, and the number operator tells us how many of them there are. So we can form that Zn of t as being trace of e to the minus beta times this number operator. And again, you can write down that for a matrix, the product from 1 to n of 1 over 1 minus t to the m is this expression. One can derive that in a rather elementary fashion a little bit later. This is given, if n goes to infinity, then it's often frequently one would like to talk about the large n limit of such systems, and to discuss what's going on in the counting in large n. And z infinity is given by 1 over the Euler function, the Euler-Totian. But the real question, as I introduced it, is what happens for multi-matrices. The eigenvalues are no longer that useful. They're going to be the invariants of one of them. I could diagonalize one of the matrices, and I've got n of the invariants, but I have many more matrices. For instance, I have x and y. I can diagonalize x, but not y. So what are the remaining invariants that one, and how should I describe them? And how many of them are there? What can one say about them? So one way of doing it, there's obviously such a question has emerged in the classical literature, and it seems to have emerged in around 1943, I think it is. I can't read what's it's in my yeah, it doesn't matter. But was rediscovered later, and it is one of the results is formulated in terms of what's called the Nagata-Higman theorem. And the Nagata-Higman theorem, I've written it out above it. It tells us that there is an important number, calligraphic n of n, which, and this is for nilpotent algebras, that n of n, which characterizes that system, and was used in the context of multi-matrices in this theorem of these guys here, and the book of processi is one of the more useful ones in this regard, and it tells us that there's a longest trace that we need to consider. And it also tells us that the invariants are the traces of matrices, of strings of matrices, and that there is a longest one, and the longest one is given by n of n. And what's known as well is that n of n is greater than n times n plus 1 over 2 and less than n squared. So that's the longest string of invariants, but it still doesn't tell us how many invariants there are. And I recommend this article of Drensky for a review of many of these things. The partition function and that counts the number of invariants was related to the Hilbert Poincaré series. It's called the Hilbert Poincaré series in the maths literature, and it can be given by this Moline-Boyle formula, which I've written out here, which is just a contour integral. And one can evaluate these ones, and Ti are formal variables for each of the matrices that one's considering. It looks relatively straightforward. The complication is that there are lots of poles. It becomes cumbersome to evaluate for more than 2 matrices, and even for even for 2 matrices, it has only been evaluated up to n is equal to 6 in terms of 2 variables and n equals 7 for 1 variable, and that was relatively recent. And the context in this setting was counting the BPS, the quarter BPS states of n equals 4 supersymmetric Yang-Hills. That was where they were interested in it. But one can do that integral for relatively small systems, and I've written out what it looks like for 2 by 2 matrices, and for 2 2-by-2 matrices, and the information that you can see in it is that it is 1 over 1 minus T1. T1 is telling us that one of the variables is the trace of the first matrix. We have T2, the trace of the second matrix, T1 squared, the trace of the first matrix squared, T2 squared, the trace of the second matrix squared, and T1, T2, which is the trace of the product of the matrices. And there are no further relations between them. It is freely generated by those ones. And you can see that the invariants are trace of x squared, we have these 5 invariants. If I take 3 matrices, we get something slightly more complicated, and there's a term on top, which is T1, T2, T3. The T1, T2, T3 does not appear as a square, so it is an elementary generator, and it corresponds to the trace of x, y, z, and it matches the longest chain that we would expect, longest string, with being 3, and trace of but its square satisfies a relation, so it's really just a Z2 variable that's in here. And what it is if you think of 2-by-2 matrices, you can think of 3 2-by-2 matrices. They form a tetrahedron, and the volume of the tetrahedron has an orientation, and that's that Z2 that's being picked up here. To go back to the quantum setting, and for Balachandran, one should always be quantum. That harmonic oscillator system that I described is given by this gauge Gaussian model, and I've taken the constant there to be 1, just for simplicity, and the covariant derivative, and I've written it as a trace, because we want to now just look at that trace of e to the minus beta times this creation annihilation operator, number operator. This action, the simplest way to derive the Mullian-Weil formula is to treat this as a lattice gauge problem and do Euclidean path integral quantization of it, discretize it, so that the derivative becomes a finite difference. It has to be matched with covariant derivatives. So I've put in my UN of the x plus 1, parallel transporting x plus 1 back to xn to match them, and then take the difference using this parallel transport, which is where the gauge field enters. And once you do that, you can rewrite the lattice version as this expansion here. And by changing variables, one can move all of the gauge transformation to one side. I'm going to skip this because I'm not going to have really time to do it, but it's in the transparency, so someone wants to look at it. And eventually one comes down to quantizing it. One has a quadratic form that had to be evaluated up here in the lattice version. One has a quadratic form in the end in terms of the x's, which had to be evaluated. Take the lattice spacing back to 0, and you get this action integral, that z is this integral over the remaining variables after diagonalizing this U, this residual gauge transformation. And one re-expresses it in terms of this Z is e to the I times U, and one recovers the Mullian-Weil formula. One can then easily derive the equivalent formula for many matrices. And again, as I said, you can do that integral in one case. So that's the context. For D-dimensional D matrices, we can recover our formal variables by putting in an mk for each of them, and T in the Mullian-Weil is then e to the minus mk times beta. And the Mullian-Weil effective action has this this expression SGG. The first term is arising from the double sum when I is equal to j. I've pulled it out. It's independent of theta. And the remaining terms, they look like Vandermon's, but some deformed one with a tk in there. And that's what the expression is. So I'm actually going to skip this because I'm going to run out of time. I just wanted to show you how this one would work if I just had one variable, a simple variable. These type of generating functions are used and this type of counting problem is used when you want to know in particle physics if you've counted all of the operators that are higher dimension operators in the standard model. There are an enormous number of them there. It's a significant problem to be sure that you've got every operator if you wanted it in treating a low energy effective action for the problem. You would like to be able to count it, and you'd like to be able to be sure that you've counted it. And these same techniques are useful in that setting. And they're standard when I've given one reference to that here. And I just wanted to show you how this counting works in the simplest setting, where one takes just a charged single variable. This is essentially a harmonic oscillator with a constraint that it should be invariant under this phase transformation. Then the partition function then is given by that what I've derived earlier, and one can write it down as Z as being this quantity, and you see that the invariants are just expanded in terms of T and T star. And that's just another way of looking at it. Okay. One wants to now just try and extract some of the physics from this. I started at 10 past, okay, 10 minutes. The problem has been mapped into one at finite temperature, and we have an effective action for it. And we're interested in a partition function. Expanding the partition function gives us our counting variables, so we can count how many there are asymptotically at large beta. That's going to tell us how the number of invariants grows asymptotically at large n, at large t. For the dimension n grows asymptotically. So if we expand it as beta goes to infinity is the low temperature limit of the system, and expanding we can expand the logarithm here. You can see that the expansion of in terms of t, I shouldn't expand the Vandermonde, but if I expand in the first term, we can re-express it in terms of mod of u n to the squared with some variable in here. And when we do this, we can re-express those variables. We can just call them an, And if we just keep n equals 1 term, we get what's called the A1 model, which is closely related to the Gross-Baade-Witten one plaquette model, which many people will be familiar with. But this one is called the A1 model, and it captures many of the features of what we're interested in. I should have said that since t is much less than 1, that we're going to capture the low temperature phase of the model by just picking the A1 term here, the n equals 1 term. At high temperatures, we're going to get a dimensionally reduced version of it. We are the lowest mode in expanding in this T1, this circle, gives us just a constant in terms of the gauge field A, and we get this single matrix model with a commutator of X times these, and we can then just rescale to pull out the dependence on beta, and we can obtain that the dimension of n, this asymptotic form at large n, grows as n squared d minus 1 log n. And one of the important things is that there's a phase transition between the small temperature and high temperature. And to see that, if I expand the van der Monde as well, I can regroup that earlier expression as 1 minus a n, and we see that a1 is equal to 1. That term for a1 changes sign, and since the a1 is given by these sum over I equals 1 to d of ti, and an is ti to the d, that same sum, it's positive, and the first one to become negative of those 1 minus an has to be a1, and it occurs at a particular temperature, which is th, which is 1 over log of d, where d is the number of matrices, and this is a Hagedorn phase transition in the system. One can formally just integrate over the UNs in this variable up here, as written, and treat the UNs as approximate continuous variables, and get z equals z infinity, and you see that it's equal to this expression here. This is in fact exact for n equals infinity, taking n goes to infinity, sitting in the low temperature phase. It gives you, this is an exact result, and you see that there's a pole in the expression when n is equal to 1. So that tells us that these coefficients, that something happens, that's where the phase transition is, and that's the Hagedorn transition. We can expand that out. We take the z infinity of t, expanding in t, we get the dimensions. So you can see that the dimensions as n goes to for n equals infinity, they grow as d to the n, which is growing exponentially. And so we have an estimate of what these dn are for small n. But this expression breaks down near the transition. So to estimate these dimensions for dn for large n, we can still use the A1 model, because the transition is occurring at beta is equal to, or at t is equal to 1 over d, and d is more than 2, or even more than, less, is 2 or more or greater. So if we we can get a reasonable estimate of what's going on in the, at finite n by focusing on the A1 model. Expanding the A1 model, we can expand it in powers of A1 and just use some group theory to re-express the partition function for the A1 model in terms of as written there. The dn give us the dimensions of the representations of the permutation group, and we can write out what they are exactly here. And we have also that 1 over k factorial dr of sk squared is 1 for k less than or equal to n. And that's just an identity. And I've just plotted some of the coefficients here for you in comparing the n equals 5 with n equals 8 in the A1 model. And you see that they cut off rather sharply not at n, where one might expect, but at a larger number. For large n, we can look at the other side of the transition, by going to a continuous variable, the density of the eigenvalues of A, which are our theta I. We can go to a continuous variable and write in terms of the effective action in terms of a density of eigenvalues. So we get S GG in terms of rho, where what I've done is I've really just taken theta n, taken it to be a continuous variable of n, and gone to a density of rho and written it as this one. And this is gives me an effective action. This is for the entire system. It isn't really solvable or hasn't yielded to a solution. But if I do it for the A1 model, one can find what the eigenvalue density is. And the eigenvalue density is given by this expression here. It's a change of variable of a Wigner semicircle, if you play with it a little bit, and you choose the variable S. But it tells us that in some of the details of the transition, that for A1 less than 1, the partition function is 1, essentially. The log of it is 0. And for A1 greater than 1, this is where the transition occurs. It is given by this expression in terms of that. We can expand it in terms of the temperature. We see the nature of the phase transition, and the transition occurs precisely at E equals 1/4. I've given you some graphs just to show you what the transition looks like. But I want to focus more on the entropy, because we're interested in counting the number of states. And the entropy, we can extract the entropy. We've got the entropy of the counting from low temperature phase from the exact expression, and taking n goes to infinity. We're getting the counting from the high temperature phase from this density, but it's only an approximation because we've used the A1 model. If we use the derivative of the entropy with respect to energy being beta, we can integrate back to get beta of E to get the S by integrating beta with respect to energy. We get that the entropy is given by this expression. And we have the entropy as a function of energy above the transition. So we can compare the two. And the transition occurs exactly at E equals 1/4. At low temperature, we have Z infinity of T and D being this one. I'm just rewriting what we saw earlier. Z infinity of T being this exponentially growing with the energy, but that's only valid up to 1/4. It's matched at S equal at 1/4, the energy being 1/4, and we get the energy being log of D over 4, and at the transition occurs exactly at n² over 4. And what it's telling us is that the transition is one where the trace relations can be ignored. We can treat the system as if it was an infinite matrix system up to n squared over 4, but not above that. And then I'm just summarizing what we found here. The dimension grows exponentially as e to the n squared log d of e below the transition. And above the transition, we get this n squared with some, as written there, and the low term, and we've matched that at e is equal to 1/4. There is no jump in the transition. We're at finite n. This is a finite n system. One can compare it with the small matrix size expansions, and it agrees incredibly well with it, actually. So these are, I can finish at this point. This is rephrasing the main results and leave it to questions. All right? Okay, thanks.
Are there any questions from the audience here? Yes. Yes, go ahead, please.
Just one small mathematical clarification. So this phi of 1 by d, so I thought that the Euler-Toten function is an arithmetic function, right? So you have to take the natural numbers as the input. What does 1 by d, phi of 1 by d mean here?
It's you don't take the natural numbers as input.
This is the Euler-Toten function, right?
It is the Euler-Toten function as a function variable. I introduced it earlier. It's the product. It's the generating. It is the partition function of. It's 1 over the partition function of the one matrix model where the variable t is e to the minus beta m, and well, this is just 1 over 5d. Is that, and it's written as it is product from t. It's phi of t. I think that's what it is.
I see.
So t is a variable there. It doesn't have to be. You can take it to be anything you want to and put it into that function.
I see. So, I mean, the one I was aware of is like all the natural numbers and then the number of numbers co-prime to it, like less than and equal to co-prime to it. So that was the Euler-Toten function, right? Yeah. Okay.
I presume it's an analytic continuation of the same expression.
I see. Yeah, of course. Yeah, it could be that. Yeah.
Yeah, in the sense that you have zeta functions, which are zeta of 2, zeta 3. It's natural to continue them to any formal variable and to their maximum range of analyticity. But this is what I mean by it.
Okay.
And this, it's really, yeah.
There is a question here. Could you?
Just a small comment. I was trying to understand NAM's equations, and it seems to me that the dimensional reduction you're doing, have you done it for f equal to star f, then the same dimensional reduction, not seems to me, you'll get exactly NAM's equations. Okay? So, you can, there you have the exact theorem that you can go back, that the transition from cell-dual equations to NAM is injective, that is, you can go backwards. Okay? This is a Hitchin result. Okay? So I am wondering whether these techniques will throw light on it. That's question number 1.
NAM's equations are for a monopole system.
No, you can start with cell-dual equations, and if you dimensionally reduce it, you end up, if you go step by step, you can reduce it to from 4 to 3 to 2 to 1.
Yes.
Okay? Say at the one level you get the monopole equations, and the level 1 you get NAMS equations.
Yes.
And it is inject, that is one way you can go backwards. Okay? That is the most remarkable thing about the matrix model reduction. Okay? That's the only model I know where the reduction can be undone, okay? In a rigorous way. Okay? I think I told you this.
You've told me that. I don't see how it could be true, but amazing things happen. I don't see how it could be true for a quantum system.
It is a quantum.
Yeah. No, but
it is
for
a quantum system.
I don't
know.
Because
This I don't
what
know.
you have done is you have reduced the system on a torus, for instance, is the one that I did it on, and I've completely thrown away all of the Kaluza-Klein modes for that.
We'll come back.
To imagine that I could recover the entire system and all of its quantum field theoretic results, I don't think that could be true.
It is not a classic quantum field theoretic result.
That's why I'm suspicious that it's... Because I have reduced the quantum field theory to a quantum mechanical system. In fact, if you reduce Yang-Mills in more than 4 dimensions, it's not renormalizable. There's no reason to believe that you can absorb all of the infinities into change of variable, into change of coupling constant. So, whereas I still get a finite matrix model.
So the thing is, I am not very clear on this issue, because in between, the Kalia's index theorem comes in. That is it quantum mechanical result or classical result? I don't. Kalia's index theorem is index theorem in 3 dimensions for the Dirac operator.
Yes.
Yeah. Is that classical quantum? It seems to me.
Well, that's a topological statement. So that topology can be rather captured, and I can imagine recovering topology and having retained the essence of the topology in a deformation retraction down to a much lower dimensional system, that the essence of the topology could be captured there. But
okay, we can talk about one more.
I think we can. Oh, yeah.
Sure.
You have another question?
Just a comment. I asked in Dublin also, have you looked at correlation functions? And whether they factorize or no in the larger limit?
The factorization of correlation functions, they do factorize.
Do you get a classical system then? So there should be a master field.
There should be a master, yeah. I remember you asked that, and I haven't. The master system really, I don't think it would capture what I was looking for here still, because.
There's no question on that. Okay. Then I think we should proceed. So let's thank Denjo one more time.
Sure.
And, oh, that's what I asked. And was there a question on Zoom? Who is monitoring Zoom? Oh. Was there a question in the chat? No? Okay, thank you. Okay, so our next speaker is Sachin Vaidya, and I forgot the title of your talk. Okay. He's going to tell us the title. Sachin, of course, is from IISc Bangalore. And, oh yeah, this doesn't quite work. To matrix model. So Sachin, please, go ahead. So, 35 plus 5.
35 plus 5.
Yeah.
Okay, it's a great pleasure to be here for BalFest, and I'd like to thank all the organizers. We missed thanking Alok, so I think I should take an opportunity to thank Alok, who's one of the organizers. And the juicy details of my interaction with Bal will be on Thursday, but the short summary of what I'll say later is that it's an honor to have Bal as a teacher and a pleasure to have him as a friend. So what I want to tell you today is about some work on the SU2 matrix model. It's fortunate that Denjo talked about matrix models, so you will see some of the things that he talked about, a few of the things that he talked about. And although the title of the conference strongly emphasizes quantum, almost all of what I will tell you today is classical, and hopefully towards the end there will be a little bit of quantum in it. This is work done with my student Chaitanya Bhatt and a summer student from IIT Bombay, Vijay Nenmali, who's now at Cambridge. Okay, so this is the plan of my talk. I will introduce the matrix model and show you that in some particular singular value like coordinates, the matrix model has a very nice description. And in particular, there is an emergent tetrahedral symmetry, which may be related to the kind of symmetry Denjo briefly mentioned, but we'll have to wait to see if it is. But what I will do is then look for classical orbits, and these classical orbits can be classified by subgroups of this tetrahedral symmetry. So we will study their stability. And as you increase the nonlinearity, because this is fundamentally a nonlinear classical system, these orbits destabilize, and they destabilize in a most interesting way. So I will use 3 tools to study the destabilization. One is called the monodromy matrix, which I'll tell you a little bit about in case, since maybe not all of us know about it. I found out about the monodromy matrix only a few months ago. I'll also, the other tool that we will use to study the destabilization is Lyapunov exponents. And finally, the tool which I discovered only recently, which I found out about only recently, but is apparently a hot topic in condensed matter, in parts of the condensed matter community, which is called small system thermodynamics. So these are 3 overlapping tools that we will use, and it's very satisfying to see that they all point to the same, they all converge to the same conclusion. And one interesting point about one of the interesting points about what we learn is about ergodicity breaking that takes place when the systems become chaotic, and the connection to, and I will make some conjectures about the connection of this ergodicity breaking to possible phases of this system. So that's what it is about. Okay, so let me start. The SU2 matrix model is very easy to describe. Denjo started off that description, but I will tell you anyway. The basic building block is a 3x3 real matrix, and it has rotational degrees, rotations, physical rotations act on it. Here I have included in physical rotations also the parity, which is why it's O3. And there are gauge rotations. So physical rotations act from the left, gauge rotations act from the right. And in terms of this matrix M, we can define an electric field, which is just M dot, and a magnetic field, which is linear in M and quadratic in M. So there is a certain history behind why the electric field, why the magnetic field is defined like this. A short, if you have a telegraphic answer to that, is that this magnetic field is nothing but the pullback of the Maurer-Cartan form to an underlying S3 on which the matrix model has been constructed. But given the electric and magnetic field, we can go ahead and write down the Lagrangian, which is just E squared minus B squared, and I've put in a 1/2 G squared, which is the Yang-Mills coupling. And with Amilcar Quiros, Bar and I looked at this model. At that time, we were interested in this model because we were interested in the statistical properties of colored states. But it turns out that this model is quite versatile. And if there's time, I can tell you what other interesting things you can do with this model. But one thing you notice immediately is that this is just quantum mechanical, or this is a model with finite number of degrees of freedom. and the potential V that I've written here is the square of B. So it has up to quartic terms, quadratic, cubic, and quartic. And so you immediately recognize that this model that I've written down is just a multi-dimensional quartic oscillator. Okay. But we can do more if we choose the right coordinates. This, of course, we know that you can always do more with the right coordinates. So in particular, if you decompose the matrix into SVD-like coordinates, that is, you choose an R on the left and an S on the right correctly, then you can write this as R times a diagonal matrix times S transpose. You can do this for any 3 by 3 matrix. And with R inverse R dot and S inverse S dot defined like this, these are essentially angular velocities. The Lagrangian has a fairly simple form. And because this matrix is because the rotations from the right are gauged, we would like to set lambda to 0. So in order to concentrate on gauge invariant dynamics. Right? So in particular, we will set lambda to be 0. And for the things that I want to tell you today, we will also look at the spin 0 sector. We will also set omega to 0. So we have gauge invariant spin 0 dynamics that we would like to look at. So if you put this ansatz M equal to R A S transpose into the formula for the potential which I had shown you earlier, then like I said, this is basically a quartic oscillator. So you can see quadratic, cubic, and quartic terms. But it's more than but there's more to it than this. There is, of course, a symmetry. For example, you can exchange any of the A's, and you can flip two signs, like A1 goes to minus A1, A2 goes to minus A2, for instance. So there is an action of S3, then there is this action of Z2 cross Z2, and it comes together very nicely as a group that is isomorphic to the tetrahedral group. So this potential has a tetrahedral symmetry in the variables A1, A2, A3. This we could not have seen unless we had gone to these singular value coordinates, and it turns out that this tetrahedral symmetry will play a very important role in understanding both the dynamics as well as chaos properties of this model. And if you extend, if you then include time reversal, then the full symmetry of the Hamiltonian is this tetrahedral symmetry times a Z2, which is the time reversal symmetry. So this is what this tetrahedral symmetry. This is a picture of what this tetrahedral symmetry looks like. So I've plotted equipotential surfaces. So if the potential is very small, 0.05, then the equipotential surface is actually made up of 5 disconnected blobs, and you can see the tetrahedral symmetry quite obviously. At a critical value, 3 by 32, the blobs connect up. So this critical value is actually the saddle point of the potential. And then you push it further, the blob just grows, and then this is sort of a generic picture at some very high value of the energy. But in any case, this is to show you what the tetrahedral symmetry looks like. Okay. And so if I go back from that Lagrangian, if I go back to that Lagrangian, construct the Hamiltonian, then this in the spin 0, color 0 sector, this is the form of the Hamiltonian. And about 18 or 20 years ago, these people identified this Hamiltonian, almost exactly this Hamiltonian, as a 3-dimensional generalization of the well-known Henon-Hiles problem. So the problem of the SU2 gauge matrix model in this particular sector is exactly the 3-dimensional Henon-Hiles problem, and this should tell us, for those of us who know anything about Henon-Hiles, this should prep us to interesting things that will that we will discover. Okay. So like I said, the disconnected pieces connect up when at some critical energy. That's the saddle of V. So I'm going to rescale my A's and P's and then work in terms of this dimensionless Hamiltonian, where my epsilon is g times e to the half. And the advantage of working with this rescaled Hamiltonian or this dimensionless Hamiltonian is that this epsilon measures nonlinearity. So for example, if when epsilon is 0, this term and this term drop off, and this is nothing but the three-dimensional isotropic oscillator. And we know that the three-dimensional isotropic oscillator has only closed orbits. Yeah. Yeah. So that's why I was careful to say SVD like. And this has to do, it is a small but an important technical point, but it is a technical point. So if it's okay, I will come back to it at the end. So, but the short answer to your question is that in the way that I have done the decomposition, A's take all possible real values, not just positive values. Now, a long time ago, this mathematician Weinstein showed that if you have closed orbits, then for small nonlinearity, the closed orbits continue to exist, and these are called nonlinear normal modes. For this particular system, this three-dimensional Henon-Heil system, people have been, mathematicians, especially those who work in dynamical systems theory, have been looking at this particular problem for a while now. So these people, Montaldi, Roberts, and Stewart, they studied and organized these nonlinear normal modes for the problem that we are looking at. And they found that they can be organized like this, essentially by the stabilizers of, by the conjugacy class of the stabilizer of the orbit. So there are these 5 classes, and these are their names, A3, A4, A3, A2, B3, B4. These are just particular subgroups of TD cross T. And one way to think about these stabilizers is they are essentially symmetries of the initial conditions. So we have 3 A's, we have to specify 3 A's and 3 P's, and some of them may be equal to each other, or some may be one may be a particularly chosen multiple of the other, and that is a sense in which these subgroups are symmetries of the initial conditions. Okay. So what we are going to do is we are going to study perturbations about each type of the orbit. So I showed you that there are these 6 types of orbits. We're going to look at perturbations about each type of orbits. And generically, as you increase epsilon, these orbits destabilize when the perturbation becomes sufficiently large. So like I said, we are going to use 3 tools to study chaos. One is this monodromy matrix. The other is to compute computation of Lyapunov exponents. And finally, some thermodynamic considerations. So I am going to focus on A4 and A3 because these have the most interesting and dramatic behavior. The other ones are interesting, but these are much more interesting. So I want to tell you only about A3 and A4 orbits. So A3 and A4 orbits, these correspond to straight line orbits. In fact, like I said, they destabilize in a most interesting way. So I will show you what happens for A3 and A4. Now, in dynamical systems theory, people routinely use this technology called the monodromy matrix, which is that you start off with some periodic solution, look at a perturbation, and look at the equation, time evolution equation of this perturbation. So that's typically of this form. X, of course, is not just the coordinate. It's a column vector of the coordinates and the momenta. Now, you can, once you have an equation like this, time evolution equation, you can then write down a time evolution operator or a time evolution matrix U, which will map x of 0 to some later time x of t. And if you evaluate U at the end of the time, at the end of the time period, or for the time period t, then U of capital T is called the monodromy matrix. And eigenvalues of U carry information about the stability or instability of this monodromy matrix. Because U is real, for instance, because U is real, the eigenvalues come in complex conjugate pairs. And an orbit is unstable if and only if one or more eigenvalue lies outside the unit circle in the complex plane. Now, for both A3 and A4, the orbits are themselves known analytically. A3 is harmonic function and A4 is an elliptic function. So we can actually do a lot of the work that people are forced to do numerically. A large amount of it we can actually do analytically, and we can gain insight in the question of stability of these orbits. And in particular, for our situation, it's enough to study this quantity gamma, which is trace U minus 2 by 2, some function of trace of U. Okay. So let me tell you what happens for the A4 orbits. So this is the initial condition that characterizes the A4 orbit. And if you look at if you do that perturbation around it, etc., the perturbation organizes itself into this, the perturbation equation, fluctuation equation organizes itself into a Whittaker-Hill equation. And this is what the Whittaker-Hill equation looks like. But one thing you notice is that it's nothing but the Schrodinger equation for a particle in a periodic potential. And these etas, alphas, and betas, these are constants that depend on A, which is my initial condition, which itself remembers the initial total energy. So the energies, so we know that for a particle in a periodic potential, even without doing any calculation, you know that there should generically be bands and band gaps. They play them, but because they are functions of A, it plays itself out in a rather interesting way. So when you have, so this eta, which is a constant that depends on A, when eta is an allowed region in the sense of a periodic Schrodinger problem, then the corresponding solution is a block wave function, and that corresponds to a stable perturbation. And when eta is not in the allowed band, then what you get is a non-normalizable solution to this equation. So that means that for this classical mechanical system, this is a perturbation that grows exponentially in time. So here, numerically, what we saw is that when energy g squared E is less than 3 by 2, then the orbit, A4 orbit, is always unstable. And then for energy greater than 3 by 2, we find repetitions of, we find repeated bands of stable and unstable regions. So this is what the monodromy matrix, the gamma looks like. So I've plotted gamma as a function of energy. For low values of energy, the gamma is greater than 2. And so it's unstable, and then it becomes stable at around at about 3 by 2, and between, in this small region, it's stable, and then it again becomes unstable, and it's stable again, and then it's unstable for a tiny region here, then again stable here, etc., etc. So there's a repetition of stable and unstable region, and it goes on and on. It just goes on and on. Here I've plotted it till energy equal to 100. And this is what it looks like if you actually plot the orbits. So this is near 3 by 2, where there was a jump from stability to instability. So if you plot the orbit in the A1, A2, A3 space for 4.999, then the orbit looks like a hairball. But if you plot it for 1.501, which is just above 1.5, then it's a straight line. And you can check that this is what happens at every place where there is a transition. So we'll have more to say about A3 and A4 orbits, but let me tell you about the monodromy matrix for the A3 orbits. So again, the idea is very similar. I'll go through this a bit quickly. So these are the initial conditions now that describe A3 orbits. You can solve for the actual orbit Again, you can solve, but now it is an elliptic function. So you again look for the perturbations, etc., etc. So again, you get a Schrodinger equation, but for a particle in a periodic potential, because this potential is a more complicated one, because the starting point was an elliptic function rather than an ordinary harmonic function. But again, we have bands and band gaps. And here we find that for energies less than the critical energy, that is at that saddle point, for energies less than the saddle point energy, our gamma oscillates between plus and minus 2 with ever increasing frequency. And these peak spacings, so the places where it destabilizes or becomes stable again, these peak spacings, they vary geometrically as we approach the critical energy from below. And the same thing happens for energies greater than EC. So again, there is an oscillation, but now with ever decreasing frequency. And the peak spacings again vary geometrically as you approach the critical energy from above. So this is what the picture looks like. So I've plotted the energies for the subcritical region. And one thing, so this is from 0 to 0.9. Then I've taken a small region here and blown it up. And then again taken a very small region here and blown it up, and so on. And I've done the same for the supercritical part. So this is from 0.09 to 0.093 to 0.09377. Then I've taken a small region here and blown it up. Well, you get the picture. But so one thing you immediately notice is that there is a self-similar behavior. And so this is again, if you like, the stable to unstable flip for A3. So if you look at this region, I think I have taken it near 0.3 up. Well, it's one of these regions, I think 0.3. So I've looked at this region. I've looked at this point here. And you can see that it's a transition from a stable to an unstable one. And so you get a straight line for some energy, and for some energy slightly greater, again, it just looks like a hairball. And you can, because it's a geometric function, you can compute the ratios of these hairbands. They are not the same on either side. We get these two incredible numbers. I call them incredible because I've never seen such numbers before. I think they are quite pretty. But what is interesting and important is that we get two different geometric constants on the two different sides. Okay, now let me quickly tell you about the Lyapunov exponents. So again, you can compute the Lyapunov exponents. So we compute the Lyapunov exponents orbit by orbit. So these are the Lyapunov exponents for the A3 type of orbits. So here, again, you see that the Lyapunov exponents are non-zero, then they become 0. Then they are non-zero, they become 0, non-zero. And these alternation between non-zero and non-zero coincides exactly with what I showed you earlier about the monodromy matrix. So these are completely consistent with the results from the monodromy matrix. And we can try to fit this curve to we can try to fit it, and it turns out that the growth is like e to the 1/4 for large E. You can do the Lyapunov exponent calculation for A3 as well. Again, A3, of course, for high energies, the bands are very, very widely spaced. So we can see only one band here. But again, the energy goes like e to the 1/4. And because the bands are very widely spaced, I'm not able to plot the next band here. But you can then go ahead and look at generic perturbations. And for generic perturbations also, you can see that the plot of Lyapunov exponents versus e to the 1/4 is a straight line. And this was a result that was, I think, first discovered in a very closely related model by Hashimoto, Murata, and Yoshida a few years ago, where they found that the Lyapunov exponents grow like e to the 1/4. Okay. So the third point so I told you about the monotony matrix, the Lyapunov exponents, and now about these small system thermodynamics. And the idea basically comes from the observation that for arbitrary initial conditions, our system is chaotic. And chaotic systems are also ergodic. So by an old theorem of Birkhoff and Khinchin, for ergodic systems, time average is the same as ensemble average, which, if you like, is one of the foundational principles of the way we do statistical mechanics. So if this is true for an ergodic, for a chaotic system, then the question is, can we adapt thermodynamic ideas to describe this chaotic system, even though it's a system with just 6-dimensional phase space? And this idea was suggested many years ago by this mathematical physicist Berdyshevsky. And the starting point is actually goes back to Gibbs. So Gibbs says that if you compute the volume of phase space less than or equal to an energy E, then you can define entropy as just the logarithm of this volume. And then you can define the Gibbs temperature as, or 1 over the Gibbs temperature as just the derivative of S with respect to E. But for ergodic systems, we have another definition of temperature through the equipartition theorem, which is that the temperature is the time average of P times del H del P. For each P, this is not a sum over P. For each I, this is not a sum over I. So there's actually many equations. And we checked numerically that we computed the Gibbs temperature and computed expectation value of P1 squared, P2 squared, and P3 squared. You can see that for low energies, there are small deviations, but for higher energies, the ergodic values coincide completely with the Gibbs temperature. So we can say that the system has thermalized. And A3 and A4, the orbits that I talked about, these are special because because of the presence of those bands and band gaps, these orbits actually break ergodicity. So you can, for A3 and A4, you can compute the Gibbs temperature and these ergodicity averages, and you can see that there are regions where they don't match. So this is for A3 and this is for A4, and these are exactly the places where you have those band gaps. So ergodicity is broken exactly in the, so this actually coincides completely, confirms fully the calculation from the monodromy matrix and from the Lyapunov exponents. So it's broken exactly in the regions where the Lyapunov exponent vanishes. And so this suggests to us that ergodicity breaking may have a thermodynamic interpretation. So this is where it becomes a little bit conjectural, but I think that we have reasonable evidence for this. So for A4 and A3, the stable orbits exist for arbitrarily high energies as long as the energies are in the bands. And if you are in the right band, then these trajectories don't explore the entire available phase space. In particular, they are confined to certain corners. So these trajectories, they clearly break ergodicity. And numerically, we have found that the equipartition theorem does not hold. So the question is whether we can interpret ergodicity breaking as phases, because it seems to us that at least from the thermodynamic discussion, such a conjecture is not unreasonable. And it's not unreasonable, it is interesting and attractive to have such an interpretation because we know that in gauge theories, there are phases that go by the name of colored glass. There are glassy phases. So it would be interesting to see whether the phases that come here from ergodicity breaking are related to glasses. Now, there are two corners of, there are at least two corners, one for A3 and one for A4 of the configuration space from which the dynamics doesn't break out. It gets stuck in these corners. So what I want to show you is some version of a Poincare section. So this arrowhead, if you like, is a particular way of representing the configuration space, and I don't have too much time to go into that, but it's a particular way of representing the configuration space. And if I take the A4 orbit, for an energy where it is ergodic, the orbit spreads over the entire arrowhead. Whereas if I take the A4 orbit at a nearby energy which is in the band, then the orbit is stuck at the top tip. It's just stuck there. And you can say it's the same statement you can make for, it's the same thing for A3, except that for the A3 orbit, when you choose the energy in the energy band, is stuck at the two tips, this tip and this tip. So it can go from, it can be at either of these tips, but it cannot be anywhere else. Okay, and so finally, because quantum is part of this title of this thing, I thought that I should say that the quantum SU2 matrix model with one flavor quark, we studied it some time ago with my student Mahul Pandey. And at that time, we found that quarks get stuck in special corners of the space of gauge fields. And in particular, we found one quantum phase where the quarks got stuck to gauge fields corresponding to this tip. And like I just showed you, the classical theory shows that A4 orbits, if they have the right energy, get stuck there. We found another phase, which is actually a color spin locked phase. And for that phase, the quarks get stuck either at this tip or at this tip, at gauge field configurations corresponding to either this or this tip. And again, I showed you that these correspond to A3 orbits with the right energy, classically. So I think I have just a minute or two left, so I'd like to end now. And yeah, I know what I wrote behind, so I can read it off from memory. So the question of what quantum signatures of chaotic dynamics is, of course, not settled. There are many answers to it, each one both attractive as well as with its own drawbacks, and there is no simple answer. But we would like to muddy the question further by adding that classical ergodicity breaking is what signals quantum phases as one of the, oh, is there something I can do, I should do? Unmute. Oh, thank you. So to this list of connections between, of the signature of, quantum signature of classical chaos, we would like to, like I said, add one more piece. And I will just leave the summary for you to look at. I won't read it out, except one point that which I didn't have time to talk about is that one of the orbits actually destabilizes via the same mechanism that Feigenbaum found, which today I do not have time to show you. So I will end with happy birthday, Bal.
The tetrahedral symmetry is only in the sector which is chosen, right? It is not in other sectors.
No,
it's not the global.
No,
for all
the tetrahedral symmetry is the symmetry of the potential. Right. So the symmetry will be there even when you move to sectors which have non-zero spin. So we are going to look at it about what happens when you turn the spin on.
Okay. The second question is, usually there is a problem between classical chaos and when you go to the quantum level.
Yes.
Transition.
Yes.
There is no quantum chaos.
Yes.
So can you tell something about it?
Yeah. So like I said here, there is no simple answer to what is the quantum signature of classical chaos. There are many suggestions, but each suggestion has some merits as well as drawbacks. all I can say at the moment is that we have only muddied the water more by suggesting that classical ergodicity braking can actually correspond to quantum phases.
Okay, I'm going to take the question from online first, and then I'll come back to you.
So there's a question from Professor Weigel. Says, nice talk, Sachin.
Hi.
The figure with the Lyapunov exponents had some isolated entries. Do they have a certain interpretation?
Yeah,
or it's just a matter of discretization?
Yeah, let me show that figure, and I will, this one, right? Is it this figure that you had in mind? So these are these I mean, are these the isolated points that you were thinking about? But I assume that they are, and these are actually numeric artifact of our numerics. So in principle, there should be if there exists an analytic calculation of Lyapunov exponents, and I haven't really seen one, they should be sharp.
Okay. Well, Kumar had a question first, and then I'll come back to them.
Was almost thermal, right? You showed.
Yeah.
So there was a good agreement. Right.
Yeah.
So what was the nature of the perturbation when this happened?
So this is for a generic orbit with generic perturbation. So it's a 6-dimensional phase space. You solve the equation of motion numerically, and then you make a then you perturb. You have the freedom to perturb all the 6 variables. So those are we are looking at the most general perturbation, and that is for those kinds of perturbations, we look at you look at an ensemble of orbits.
So if you, in this situation, if you play with the perturbations, I mean, if you make it bigger, smaller, or various things, when does this behavior start to depart from thermalization?
So if you make a generic perturbation, you miss ergodicity braking. This is why group theory has turned out to be in fact, we arrived at pictures like this fairly early on in the game, and it's only after we discovered the work of Montaldi, Roberts, and Stewart that we realized that group theory provides us with a much more subtle tool. So if you use group theory to study orbits, then for A3 and A4 and for other orbits too, you make a full 6-dimensional perturbation, but for A4, it turns out that the orbit is stable. So even if the perturbation is 6-dimensional, the orbit continues to be a straight line, provided you have chosen the energy to be in the stable band. So then that is a situation which we describe as ergodicity braking, because even the most general perturbation can't knock the orbit off.
So even the most general perturbation would show this thermalization behavior?
Most general perturbation will show this thermalization behavior, yes. And then for A3 and A4, this is what you will see.
Okay, thanks.
For the most general perturbation for A3 or A4.
Okay. Then Joe, and then Bob.
Your system, as I understand it, is one of 3 vectors in 3-dimensional space. And I think your A1, A2, and A3 are the lengths of the 3 vectors. Your potential involves the...
That's right. I don't want to call them vectors. Let me call them variables, because they do not transform.
If you think of them, I mean, as the matrix says, your 3 by 3 matrix is really...
These are the 3 singular values. These are, if you like. Roughly speaking, these are the 3 singular values.
I think they have to be the lengths of the 3 matrices.
What do you mean by lengths of
lengths of the 3 vectors? Because your 2 by 2 matrix is you have an SU2 Yang-Mills.
Yes,
which means that you started out with 3 2 by 2 matrices.
Yes,
which is equivalent to 3 vectors in 3-dimensional space.
Yes,
and those vectors are, I think you've restricted yourself.
The set of all possible 3 vectors in 3-dimensional space.
3-dimensional space, yes. But you're not allowing them to rotate you chose an angular momentum 0.
Yeah, we have chosen
so,
angular.
So there's no overall rotation. So you just have the oscillations of the three vectors, and I think
Yes.
one of them you had them three of them aligned. Was it your A?
Maybe you want to see the Hamiltonian?
Oh, I remember the Hamiltonian.
Okay, what is there a particular
it's
graph
your-
or
it's
equation
your
you want to see?
variables, your different sector. I think that the three vectors are aligned, and you're doing some perturbations about them.
This one? Are you talking about
Yeah,
this?
you had one of them which only A1.
Okay.
Sorry. Oh no, that was the one.
This one? Well, tell me your question and I will find the right slide.
My question is, can I visualize what is it? Can you visualize what's going on with the different ergodic systems in terms of the three vectors? Because I can orient one of the vectors to them pointing north, and then I have just two vectors rotating around. But they're not rotating; they're just oscillating.
I suppose so. I haven't thought about it like that.
Maybe we can talk.
Yeah. I'm sure that it will teach us something.
Is that a follow-up to Dennis' question?
Okay.
So you have to, A4 is a particular finite dimensional group. So, no. This, the label A4 is not supposed to mean alternating group. I'm sorry that the people who came before me chose these names. I would not have chosen A4.
I see.
So,
So that is
it's not an A4 is
it's
this
a
guy.
D2 cross something, right?
Yeah,
Tetrahedral symmetry, the table which you showed.
I'll show you.
Yeah, so this is the.
This is,
How do you also see that the number of orbits is 3 for such a breaking? Do you see it? Or
the so you can choose the capital A that I had chosen. You can choose it in the first slot, or the second slot, or the third slot.
Okay, so that way.
That
that initial condition is not specific. You could have A 0
Yeah,
0 or 0
yeah.
A 0.
But under tetrahedral symmetry, you can go from one.
I
I don't know how these things connect to the quantum system, but if you take, for example, the two torus, okay? In the two torus, if you, one can write down a self-adjoint operator which evolves on the two torus, but the direction of the evolution on the two torus is an orbit which is not periodic, so it becomes ergodic on the two torus.
Yes, yes.
So that is that will be good. However, this is, but there is no fixed point here.
Yes.
Because it's a unitary evolution. So there are fixed points because there are stable orbits. You just have to change the time evolution from this ergodic orbit. You have to change some parameters. It will get fixed, but then it will again get fixed because of unitarity. But how do I go from one to the other? For example, can I say the stable orbit is stable? Can I make a perturbation? What issue? How do I make the perturbation? Okay? Unitary perturbations will do nothing. Okay? It seems that the appropriate quantum situation is a POVM, that is positive operator valued measure. If you do that, it appears that such orbits can get perturbed, and it may be stable, unstable, and probably one can classify the whole Tom class in this situation, it seems. Now, I want to make the final remark that I don't know how this ergodicity reflects in quantum system, but I'm sure that in QCD, the super selection sectors which you mentioned, for an appropriate chemical potential in the QCD Hamiltonian, the action on the superselection sectors or this unitary Hamiltonian is ergodic, and there are fixed points also, and it appears that they definitely have measurable consequences, which one can outline. It is not that because these are infrared effects, you see nothing. That is not true. Okay? There are actual experimental effects. Now it appears that in this context, even let's say POVM, one can then study these orbits in terms of your phase transitions. The POVM will test whether a particular stable orbit, stable point is in fact stable under the POVM.
Okay.
I suspect that these two things look very similar, but not exactly.
Okay. I think this requires more discussion. I think Sujay had a question. No.
Okay, then let's thank Sachin one more time, and we'll close the session for the morning. Lunch outside. So there is lunch outside, and when do we meet again? 2 o'clock. Okay, so we are back here at 2 o'clock. It doesn't work. Hello?
You long distance, not.
Oh, okay.